welcome everyone to join the AFOMP School webinar this time. And for this time, we are talking about a very special radioisotope technology of BNCT. The BNCT is getting more and more interesting recently. So it's really lucky for us to invite a group of researchers from Japan to give us a topic on BNCT. So first, I would like to introduce our moderator today. It's Dr. Shigekazu FUKUDA. He's the Deputy Director of the Department of Information Technology and Management in the National Institutes for the Quantum Science and Technology. Currently, Dr. Satoshi is the chair of the science committee of AFOMP. So I would like to give my microphone to Dr. Fukuda. Please, Dr. Fukuda.
Okay, so thank you, Dr. Jean. So I'm Shigekazu Fukuda, Chair of Science Committee of AFOMP and President of Japan Society of Medical Physics. I'm glad to invite three sophisticated lecturers from Japan. And first speaker is Dr. Yoshinori SAKURAI. He belongs to he is Associate Professor, Institute for Integrated Radiation and Nuclear Science, Kyoto University, Japan. So please, Dr. Sakurai, please share your presentation.
Okay, thank you.
Okay, please, okay. Please start. Yes.
Okay. Thank you very much, Dr. Fukuda. I am Yoshinori Sakurai from Institute for Integrated Radiation and Nuclear Science, Kyoto University. So my topic is Introduction of BNCT. So I will start. Sorry. Okay, so first introduction. So neutron capture therapy is a unique radiation therapy in which neutron reaction is skillfully utilized. First, a nucleus with large neutron absorbing cross-section is took into tumor cells. Second, neutrons are irradiated to the target part. Then the tumor cells are destroyed by the heavy charged particles generated due to the reaction of nucleus and neutron. As an NCT nucleus, only boron-10 is used in clinical trial. So this therapy is usually known as boron neutron capture therapy. Okay, so the world's first clinical irradiation for BNCT was carried out using a neutron irradiation field for BNCT installed at the research nuclear reactor in United States in 1951. After this year, until 2012, BNCT has been performed only using reactor-based irradiation systems. In early 2009, the world's first accelerator-based system for BNCT clinical irradiation, cyclotron-based epithermal neutrons, was completed at our institute. The clinical trial using this accelerator system was started in 2012. The development of the accelerator-based irradiation system for BNCT is energetically performed by various groups in the world. At present, BNCT using various accelerator-based irradiation systems are carried out at the plural facilities in the world. So, in my talk, so first, I will talk about the principle for BNCT briefly. And second, the history of the reactor-based neutron sources are illustrated. And third, if I have time, the history of BNCT at our institute is introduced. So my topic is mainly for reactor-based BNCT. So for the accelerator-based BNCT, Dr. KUMADA will talk on the third presentation. Okay, so next, the principle of BNCT. So this slide shows the principle of BNCT. As explained in the earlier slide, the therapy is performed according to two-step procedure. Injection with a tumor localizing drug containing boron, and second, irradiation with thermal or epithermal neutrons. These reactions are utilized. The ranges of the alpha particle and lithium-7 particles are approximately 8 and 5 micrometer, respectively. So, in principle, BNCT is a non-invasive therapeutic modality for treating locally invasive malignant tumors. So, this slide shows the boron-10 compounds. So, these kinds of boron-10 compounds are used in the present BNCT. One is BSH, so the name is very complicated. So, we usually call it BSH. And one is BPA, the other is BPA. So, this BPA is para-boron-phenylalanine. So, these compounds are taken into tumor cell about 10 to 5 ppm for boron-10. In actual, those go into not only tumor cell, but also into normal cell. The ratio of boron-10 concentration in normal cell to that in tumor cell is about 1/10 for BSH and 1/3 for BPA. The boron-10 concentration and its distribution are one of the main factors for the therapeutic selectivity and the application limitation in BNCT, as well as neutron beam quality. So this slide shows the neutron reaction cross-section of boron-10. So, the neutron absorbing cross-section of boron-10 is larger for the lower neutron energy. Intuitively, the lower energy neutrons, usually thermal neutrons, are most suitable for BNCT. This slide shows the neutron reaction cross-sections of hydrogen and nitrogen. So hydrogen and gamma reaction of hydrogen and scatter, elastic scatter of hydrogen and NP reactions of nitrogen. So the incident thermal neutrons are scattered and diffused due to hydrogen in human body. So thermal neutron flux reduces relatively rapidly at the shallow part in the body. Then thermal neutron irradiation is available for shallow-seated tumors, but it has a limitation in the application for deep-seated tumor. From some experiences, it is thought that the treatable depth is about 5 centimeters from the surface using the thermal neutron irradiation. Incidentally, in Japan, so the thermal neutron irradiation has been used for deep-seated brain tumor with the craniotomy, namely under surgery irradiations. At the old time. So when epithermal neutron irradiation is applied, the thermal neutrons which are generated from the thermalization due to the scatter and modulation by hydrogen in human body. The mean free path of epithermal neutron or scatter in human body is almost 2 times longer than that of thermal neutron. And epithermal neutron is scattered several times to become thermal neutrons. Then the distribution of thermal neutron flux in human body due to epithermal neutron irradiation has a peak at the 2 to 3 centimeter depth from the surface. So this slide shows the thermal neutron flux distribution in the body by depth distribution by thermal neutron irradiation. So thermal neutron flux decreases rapidly near the surface. And this slide shows the thermal neutron flux distribution for incident neutron energies. So, violet curve is for thermal neutron, and epithermal neutron, and from the this violet curves, so the first neutron irradiation. So busy slide, busy graph. So the larger the incident neutron energy, the flatter distribution of thermal neutron flux. So in terms of flatness of distribution, the higher the incident neutron energy is better. So do you think so? This slide shows the karma factor for neutron energy. So red curve is a karma factor for maybe brain tissue. Okay. So the neutron karma factor for tissue is lowest at a few tenths of electron volt, and it increases monotonically whether the energy is higher or energy is lower. Below a few tenths of electron volt, contribution from the nitrogen NP reaction is large. Above a few tenths of electron volt, the contribution of hydrogen elastic scattering is large. So whether the neutron energy is lower or higher, the dose by the incident neutrons themselves is neutrons themselves is larger. So this slide shows the absorbed dose rate distributions for incident neutron energies. So green curve is for epithermal neutron irradiation, and from the violet curves from the first neutron irradiations. So when irradiating first neutrons with an energy of almost 10 keV, so or more, the dose delivered by the neutrons themselves is very large. The light blue curve is for the epithermal neutron irradiation. So this energy range is almost 1 keV to 10 keV. But the violet curve is for the energy of from almost 10 K, more than 10 keV. So in BNCT, the reaction between thermal neutrons and boron 10 is utilized to achieve selective treatment of tumors. From the perspective of reducing the dose delivered to normal tissue as much as possible, it is necessary to suppress the dose delivered by first neutrons, which impairs selectivity. Okay, so this slide shows the karma factor again. So finally, so thermal neutrons and epithermal neutrons can be used in BNCT. In BNCT research field, thermal neutron is defined to be less than 0.5 electron volt. And epithermal neutrons is from 0.5 electron volt to 10 kilo electron volt. And first neutron is divided to more than 10 kilo electron volt. So the BNCT neutron irradiation system is designed to minimize the mixing of gamma rays as well as first neutrons. Okay, so next, I will talk about the history of reactor-based BNCT. This figure shows one of the reactor-based neutron source. This neutron source is our facility, Kyoto University Reactor Heavy Water Neutron Irradiation Facility. This is a reactor core and neutron moderator and gamma shield. So the thermal and epithermal neutrons can be obtained by moderating and filtering fission neutrons from the reactor core uranium, almost 2 mega electron volt in average. Also, the incidental gamma rays should be decreased as possible using gamma ray shielding materials. So the reactor-based neutron source consists of source, filter, and moderator, and reflector, and gamma ray shield. So almost the same as accelerator-based neutron source. Due to the modulation, the obtained neutron energy spectrum is continuous, like this, as shown in this graph. So this graph shows the neutron energy spectrum from the reactor-based neutron source. So monoenergetic neutron source is unrealized, and mixed irradiation field of the wider energy neutrons up to a few 10 mega electron volt is obtained from the reactor-based neutron source. For the thermal neutron irradiation field, so heavy water, graphite, and so are usually used as filter and moderator. And bismuth and lead, bismuth or lead used as gamma ray shield. For the epithermal neutron irradiation field, the filter and moderator aluminum fluoride, sulfur, and so weak. We have many choice for the filter and moderator material. As thermal neutron filter, lithium fluoride, cadmium, and so on are used. And for gamma ray shield, bismuth or lead are used. So in actual neutron irradiation fields, the mixture of high energy neutrons and gamma rays cannot be perfectly avoided. Further undesirable for BNCT. The recommended values for design of epithermal neutron irradiation field, of which are described in advances in polon neutron capture therapy. This book produced by IAEA in 2023 as this table. So the ratio of thermal to epithermal neutron flux is less than 0.05. And the ratio of first neutron dose and epithermal neutron flux is less than 7 times 10 to the minus 13 gray square centimeter. And the ratio of gamma ray dose is less than 2 times 10 to the minus 13. And the epithermal neutron flux is more than 5 times 10 to the 8 square centimeter per second. So this table shows the basic characteristics of the main reactor-based neutron sources. So very busy tables. So Kyoto University reactor, JA reactor, and Brookhaven medical reactor, and Massachusetts reactor, and and this line is for thermal neutron flux and epithermal neutron flux, and the ratio of first neutron dose and the gamma ray, the ratio of gamma ray dose. So these values. So the below line is for recommended values. So some parameters of the some reactor-based neutron sources don't meet the specified recommended values. Incidentally, so the previous value for first neutron contamination, so the ratio of first neutron, those described in TechDoc 21 to 23 was less than 2. Only 2. So it was more difficult to clear the old recommended value for the first neutron contamination in the epithermal neutron sources. Okay. So that so the history of the from 1936 to 1961. So in 1936, the principle of BNCT was proposed by Lochia. In 1951, the world's first BNCT was carried out at Brookhaven National Laboratory in the United States. So in this time, so the thermal neutron irradiation was applied. Because of the problems in the Bolton compound and the quality of the neutron beam. So at that time, so Bolton compound is not BSH and or BAPA. So they did not have good Bolton compound. So the treatment results were not so good. Then the BLCT clinical irradiation was stopped in 1961. Totally 63 clinical irradiations were performed at Brookhaven and Massachusetts Institute of Technology. So this slide shows the Brookhaven graphite research reactor. So this is the first reactor applied of BNCT in 1951. So this reactor power is 28 megawatt, and so this is so very old photographs. So like maybe so here is so maybe here is a patient like this. So this is a maybe mirror. So patient is under this area. So 28 BNCTs were performed for brain tumor using this reactor. And from 1959, the fundamental study was started in Japan. In 1968, the BNCT clinical irradiation was started at Hitachi Training Reactor. Through 1996, over 200 BNCTs were performed at Musashi Institute of Technology Research Reactor, Kyoto University Reactor, and Jaeli Research Reactor. In 1987, the first clinical irradiation for malignant melanoma in the world was started. Only thermal neutron irradiation could be available in these reactor-based systems, so BNCT was applied to malignant melanoma and brain tumors with coronary artery. So this slide shows the Hitachi Training Reactor. So the first reactor for BNCT application in Japan. So this reactor power is only 0.5 megawatt, and only 13 BNCTs were performed for brain tumor from 1968 to 1974. So this reactor is so of course shut down already. This slide shows the Musashi Institute of Technology Research Reactor. So for this reactor, so the reactor power is also 0.1 megawatt. And also, using this reactor system, so more than 100 BNCT trials, clinical trials for brain tumor and malignant melanoma were performed. In 1994, the epithermal neutron irradiation field were completed at Brookhaven National Laboratory and Massachusetts Institute of Technology, and then the BNCT clinical irradiation was restarted using the epithermal neutron irradiation. In 1999, the clinical study was finished at Brookhaven because of the shutdown of the reactor. In 2000, the reactor was remodeled at MIT. The uranium converter was installed. After 23, the clinical study was stopped at MIT. So this slide shows the Massachusetts Institute of Technology nuclear reactor. So here is the fission converter for the increasing of epithermal neutrons. So Using this reactor systems, almost 30 BNCTs were performed for brain tumor. And so this slide shows the Brookhaven Medical Research Reactor. So, so using this reactor system, so almost 50 BNCTs were performed for brain tumors. Also in Japan, the epithermal neutron irradiation field was studied concurrently to the clinical study using the thermal neutron irradiation field. In 1995, the irradiation field of Kyoto University reactor was remodeled, and the epithermal neutron irradiation became available. In 1998, the neutron irradiation field for BNCT was completed at Jaili reactor number 4. The concept is almost the same as that of Kyoto University reactor. In 21st, the clinical study using epithermal neutron irradiation was started at Kyoto University reactor, and in 23, it was started also at Jaili reactor. So this slide shows the Kyoto University reactor. This reactor is installed at our institute. So this reactor power is 5 megawatt, and we have aluminum and heavy water filtered moderator systems. So through 2020, almost 600 BNCTs are performed using this reactor system, mainly for brain tumor, head and neck tumor, malignant melanoma, lung tumor, liver tumor, and so on. And this slide shows the Jaili research reactor number 4. In this reactor system, so they used filtered aluminum and heavy water as filtered moderator. Through maybe 2010, more than 100 BNCTs were performed for brain, head and neck tumor, and so on. In 1990s, the epithermal neutron irradiation fields were completed at high flux reactor in Peten, in Netherlands, and at FIR1, also in Finnish, Finland reactor in Finland. The clinical irradiation was started at HFR Peten in 1997 and FIR1 in 1999. After 2000, the clinical study was started in Czech, Sweden, Italy. So in 25, the clinical study was finished in Sweden. And in 2012, the clinical study was finished at FIR1. So this slide shows the high flux reactor at Peten in Netherlands. So this the reactor power of this reactor is very high, so almost 50 megawatt. And the filtered moderator part is very complicated. So they used aluminum, titanium, sulfur, argon, and so on. So using this reactor system, maybe almost 30 BNCTs were performed for brain tumor. And this slide shows the Finnish research reactor. Well, so the reactor power is only 0.25 megawatt. And so they developed the new filter modulator materials. They called it FUETAR. So 69% aluminum fluoride and 30% aluminum and 1% lithium fluoride. So this is a good material for filtered modulator. So through 2011, 314 BNCTs were performed for brain tumor and head and neck tumor. So from the early 1990s, the fundamental study has been performed in Argentina, South Korea, Taiwan, China, Thailand, and so on. In 23, the clinical irradiation for malignant melanoma was started using the mixed irradiation of thermal and epithermal neutrons in Argentina. In 2010, the clinical irradiation for head and neck tumors started using epithermal neutron irradiation in Taiwan. So this slide shows the GFA open pool reactor in Taiwan, so Taiwan, the National Tsinghua University in Taiwan. So they also use aluminum and fluorine as filter and moderator materials. At present, maybe more than 30 for BNCT, I think that more than 50 BNCTs were performed mainly for head and neck tumor. And this slide shows the in-hospital neutron irradiator in China Institute of Atomic Energy and Beijing Capture Technology Corporation in China. The reactor power of this reactor is 30 kilowatt, and they used these materials, aluminum and aluminum oxide, as a moderator material for epithermal neutron irradiation, and they also have thermal neutron irradiation port. So they use graphite as a filter and moderator. So using this system, they perform malignant BNCT for malignant melanoma. So this slide shows the summary of the reactor-based neutron sources in the world. So institute name, country, reactor name, and power, reactor power, and neutrons, and clinical trial, number of clinical trials, and period. So BG are slides. So North America and South America, and Europe, and Asia. So in North America, they performed BNCT at 2 facilities. So almost 150 clinical trials were performed. In South America, so only Argentina, they performed almost 10 clinical trials. And in Europe, totally almost 400 clinical trials using these reactor-based neutron sources. And in Asia, almost 800 clinical trials using these reactor-based systems. So this is a world map. Now, as shown in this map, using 21 reactor-based sources, nearly 1,400 BNCTs were performed in the world. Finally, I will introduce about the history of BNCT at our institute shortly. So this slide shows our BNCT facility. So we call this facility is Kyoto University Reactor Advanced Irradiation System for BNCT. And the facility name is Heavy Water Neutron Irradiation Facilities. This is the reactor, and this is a heavy water tank, and irradiation room, and patient setting room. So this photograph is for BNCT for brain tumor and BNCT for head and neck tumor. So this slide shows the detail of the heavy water tank. So in the heavy water tank, we have epithermal neutron modulating area consists of aluminum and heavy water. And we have a spectrum shifter system. So using this system, spectrum shifter system consists of 4 small tanks of heavy water. using this system, and we have thermal neutron filters made of cadmium. So using this spectrum shifter and thermal neutron filter system, so we can use the several neutron irradiation fields with several neutron energy spectra, various neutron energy spectra. So usually we use the only three neutron irradiation modes. So blue line is for epsilon neutron irradiation mode, and black line is for thermal neutron mode, and red line is for mixed neutron irradiation modes with thermal and epsilon neutrons. The first clinical study for boron neutron capture therapy at our institute, our facility, was performed in May 1974. The BNCT clinical irradiation at this facility regularly started in February 1990. So only thermal neutron irradiation could be available. So BNCT was applied to malignant melanoma and brain tumors with coronary artery. And from 1995 to 1996, the reactor-based facility was remodeled. The BNCT clinical study was restarted in November 1996. BNCT was applied to malignant melanoma using thermal neutron irradiation and brain tumor with coronary artery, mainly using the mixed irradiation. In December 21st, the first BNCT for oral tumor in the world was carried out using epithermal neutrons. In June 22, BNCT for brain tumors without coronary artery was started. During 5 years until the reactor operation was stopped for the fuel change, 193 BNCTs were carried out using this facility. In 25, the wide application was promoted for the cancers of body parts such as liver, lung, and so on. So during the reactor operation stop, some minor changes of our reactor-based facility were carried out. In 29, the world first cyclotron-based irradiation system, we call it CBASE, practical for BNCT was installed at our institute. So this name is our old name of our institute. So this is CBASE machine. So and this slide shows the our CBASE. So in this system, so we use accelerator the proton energy. Proton is accelerated to up to 30 mega electron volt, and so the moderated part is very complicated. Okay, so in May 2010. The BNCT clinical irradiation was restarted using the reactor-based systems simultaneously with the restart of the reactor operation. After the restart, 243 BNCT irradiation have been carried out as of January 2020. So this graph shows the accumulated number of BNCT studies at our institute. So here and here, so the accumulated number is increased rapidly. So for the wider application of BNCT. Sorry. Okay. Sorry. So the share for the tumor type has been largely changed because of the wider applications. In 25 to 26, so almost the brain tumor and head and neck. But 2010, so the share of the other part, such as body trunk part or lung or liver, so increased. And at the 2011, so the share is almost the same for brain tumor, head and neck tumor, and lung tumor, mainly miscellulomas. So, okay, conclusion. So, since the world's first clinical radiation for BNCT was carried out in 1951, the reactor-based neutron sources have been working. Using 21 reactor-based sources, more than 1,400 BNCT were performed in the world. Recently, the shutdown of the research reactor occurs successfully. So, for our reactor, so maybe so next year, so our reactor also will also be shut down. So now, so at present, the only 3 reactor-based systems used for available for BNCT clinical studies. So one is so Argentina, and one is Taiwan, and one is China. So, however, so there is a few plans for reactor-based BNCT neutron source, such as Maria reactor in Poland and some countries, such as Thailand, so also has a plan for reactor-based BNCT systems. So shifting from reactor-based BNCT to accelerator-based BNCT is rapidly advancing. However, reactor-based neutron sources are needed for the time being, especially for the basic researches. Thank you for your attention.
Thank you, Dr. Sakurai. Yeah, so any question and comment? If so, you have a question and comment, please pass your comment and question to the chat. Okay. So already, as you already mentioned, I have one question. So is there any plan to build a new research reactor somewhere in the world in near future?
Yes, maybe some plans. So, for example, so in Thailand, so they have a plan. They have a plan. So in Thailand, so the Suranari University of Technology, they have a plan to build the reactor-based BNCT systems in Thailand. Maybe so near future. Maybe so 2 or 3 years after later. So and in Japan, so we have also the new research reactor. So we have also a plan for new research reactor, but maybe so more than 15 years later. So very
15
future
years
plan.
later.
15 years. So maybe so so maybe so some countries in the world, so they have a plan to build the reactor-based systems. So I don't know the details. Sorry.
Okay. There is one question. What is the advantage of cyclotron-based BNCT than reactor?
Oh,
Yeah, basic question.
Basic system also. So for our institute, so our cyclotron machine is more, the intensity is more than our reactor-based system. So the irradiation time is so short. and the neutron energies are little larger, little higher for the accelerator-based system. So the treatment limitation, treatment depth is a little larger compared with our reactor-based system. Okay.
You. So reversely, reactor has some advantage than the accelerator BNCT. So do you have any comment?
Oh, yeah, maybe the reactor the reactor-based system is very stable,
Mm-hmm.
but the accelerator system is sometimes stopped or so and sometimes we change the target. So maintenance and running cost is maybe so the reactor-based facility has advanced compared with the accelerator-based system, but the regulation is very severe for reactor-based system. So it is very difficult to say which is a better system. Sorry.
So another important aspect of the BNCT is development of medicine, chemical medicine, including boron. So is there any development of boron drug other than BSH and BPA?
Yes, some researchers who are chemical researchers are developing the new boron compound, new boron agent. But maybe sometimes they develop the very nice compounds, but it is difficult to start the clinical study for human. So because clinical trial so the law of the clinical trial so very severe in Japan. So it is difficult to start the BLCT using the new boron compound. But some chemical researchers are developing the new compound.
Okay. Thank you very much, Dr. Sakurai. Okay,
You're
so
welcome.
I'd like to move to the second lecture. And Dr. Nakamura, so he is a medical physicist of Division of Radiation Safety and Quality Assurance National Cancer Center Hospital in Japan. I asked him to make lectures on the from the clinical aspect of BNCT. So please start, Dr. Nakamura.
Thank you for introducing me, and thank you for giving a presentation time. My name is Satoshi Nakamura. I'm from National Cancer Center Hospital. Today, I'd like to talk about BNCT in practice. This is today's outline. There are three topics. First topic is introduction about in our hospital. Second topic is a clinical trial of accelerator-based BNCT system for skin and thoracic tumors in our hospital. The last one is the implementation accelerator-based BNCT system into hospital. Now, first I talk about introduction about NCCH. Our hospital is the largest hospital dedicated to the cancer treatment in Japan. We perform 2,500 patient treatment with medical rhinite or brachytherapy every year. Our radiation oncology department has various treatment modalities. 5 medical rhinites, 1 MR guided rhinite system, 4 treatment planning CT, 1 remote after-loading system for high-dose rate brachytherapy, 3 types of the radionuclide for low-dose rate brachytherapy, one BNCT, and 3 types of the radioisotope therapy, such as the lutetium, iodine, and the copper. The member of in our department is 55. We have 12 medical physicists with 2 specialist medical physicists, 4 medical physicists, 4 medical physicist resident, and 2 trainee. And we have 10 radiation oncologists, 27 therapists, and 6 nurses. This is the overview of the BNCT facility. Treatment room is located at second basement, and the accelerator room is the first basement. The feature of our system is using the solid lithium target and the virtual beam port. This is the cross-sectional view of our BNCT facility. BNCT treatment room is located here, and the 2 medical linear accelerator system is located close to the BNCT treatment room. This is the picture of the treatment room. Left picture shows the actual treatment posture using our system, and right picture shows the maintenance work for lithium targets. This picture shows the accelerator room. The size of the accelerator room is 2 by 8 meter, and the accelerator length is approximately 8 meter. This is the schema of our BNCT system. Proton was accelerated up to the 2.5 MeV, and its proton current for clinical use is 12 milliampere. The protons were bended to the treatment room, and then those were delivered to the solid-state lithium target, and we can generate the neutron for BNCT. However, the generated neutron is too high for BNCT, so we decelerated the generated neutron using the moderator made of magnesium fluoride. Its thickness is 24 centimeter. After then, we can get the ideal neutron energy for BNCT. In our system, neutron beam control is performed by the proton charge, which was measured with the ammeter equipped in the accelerator. Expected radiation time for BNCT is less than 1 hour. Maximum thermal neutron flux is 1.4 by 10 power 9 per square centimeter per second. The lithium target lifetime is 2.5 10 power 6 millicuron radiation. After them, we have to change the new lithium target. And we can perform the 50 patient treatment in one target. This is the timeline of our BNCT project. Our project starts at October 2011, and at March 2015, we start the installation work of accelerator, and after 1 year, we can start the operation of the accelerator-based BNCT system. At February 2017, we start the non-clinical trial, and after 2 years, we finish the non-clinical trial. And after a half of a year, our clinical protocol passed the IRB in our hospital. And next month, we can start the phase 1 clinical trial for a patient with angiosarcoma and melanoma. In this month, we can treat the first patient. April 2022, we complete the patient recruitment of phase 1 clinical trial. At November 2022, we started the phase 2 clinical trial only for angiosarcoma patients. At December 2023, based on our phase 1 clinical trial result, our system was designed as an orphan medical device and drug for angiosarcoma from Japanese FDA. And September 2024, we complete the patient recruitment of phase 2 clinical trial. At this month, September 2024, we start the new phase 1/2 clinical trial for thoracic tumors such as esophagus, lung, and breast cancer. Now we talk about these topics. The accelerator-based BNCT system can be divided into two types based on the target material. One of them is lithium, the other is beryllium. We adopt the solid-state lithium target, and its thickness is 0.1 millimeter. Accelerated proton energy is 2.5 MeV, and the maximum proton current is 20 milliampere. Advantage of our system is that the generic neutron energy is low. Therefore, the neutrons can be easily moderated to the ideal energy for BNCT. On the other hand, this one advantage of the system is melting point is too low, although the thermal load to the target lithium target reaches the 50 kilowatts, and the inducing radionuclide of beryllium-7. There are three strategies for removing thermal load on the lithium target. One of them is the cooling system. A water of 250 liters per minute rolls into the target basement. Second is the incident angle of the protons. It is 30 degrees against the lithium target to increase the incident area of the delivered proton on the lithium target. The last one is the proton beam is adopted. The diameter of proton beam is approximately 10 centimeters. To develop accelerator-based BNCT system as a medical device, we validated the safety and efficacy of the accelerator-based BNCT system through the non-clinical test and clinical trial. Generally, non-clinical trial tests can be divided into two types. One of them is the physical property, and the other is the biological property. In general, physical property is described in the IEC national standard. However, in BNCT, it is not established yet. So we discuss the regulatory authority based on the IEC national standard for particle therapy. Therefore, concerning the feature of BNCT, evaluation item was proposed and conducted. Next topic is the clinical trial of accelerator-based BNCT system for skin and thoracic tumors. We talk about these topics. And this is the phase 1 clinical trial outline. in our hospital. Basic objective is the safety, and the study design is the single arm and open label study. Target disease is skin melanoma and angiosarcoma. Estimated enrollment is 9 participants, 3x3 study design. Investigational device is CICS1, and the drug is SPM011. It was BPA. Major inclusion criteria is a patient with primary cutaneous malignant melanoma or angiosarcoma diagnosed histopathologically without lymph node or distant metastasis. Patient with a superficial skin lesions whose maximum diameter of the target lesion is 15 centimeter or less. Patient with lesions that are lying 6 centimeter or less from the skin surface to the deepest part of the tumor. Patient with lesions in the head, neck, chest, or extremity, and the patient who don't have apparent abnormal hematological and biochemical values in the latest screening test within 28 days of registration. This is the major exclusion criteria. The patient with obvious disseminated lesions, patients who have undergone previous treatment of radiotherapy exceeding 75 gray for the target lesion. Patients with active lesions and active multiple cancers in addition to the target lesion. Patients with infections that require systemic treatment. Patients with active implemental medical devices, such as the pacemaker, and so on. A patient with a history of BNCT treatment. This slide shows the conventional radiotherapy for angiosarcoma. Angiosarcoma is a rare tumor. In Japan, 300 cases are diagnosed in every year. Half of their cases is elderly patient with cutaneous tumor. Primary treatment strategy for them is radical resection followed by the post-operative radiotherapy and or chemotherapy. This figure shows a case of severe dermatitis after conventional radiotherapy for angiosarcoma. This advantage in conventional radiotherapy is large field, long treatment period, which it was approximately 6 to 7 weeks, and frequent severe dermatitis and difficulty of irradiation in case of recurrence. Response rate in conventional radiotherapy is 50 to 70%. Furthermore, the rate of adverse event for skin is in all cases with grade 2 dermatitis and 66.7% with more than grade 3 dermatitis. Therefore, a new treatment method for angiosarcoma is required. This slide shows the result of phase 1 clinical trial for angiosarcoma and melanoma. The phase 1 clinical trial includes 9 angiosarcoma cases and 1 melanoma case. Left side figure shows the first angiosarcoma patient before and after BNCT. Right side figure shows first melanoma patient before and after BNCT. For angiosarcoma, response rate in BNCT is 70%, while it was in conventional radiotherapy is 50 to 7%. Furthermore, advanced event with grade 3 is more than grade 3. The MTT in BNCT is 0%, while that in conventional radiotherapy reaches 66.7%. Based on this result, our system are designed as orphan device and drug for angiosarcoma from Japanese FDA. This is a slide shows the other two cases for angiosarcoma BNCT. Temporary alopecia can be observed, but it was relieved within 1 year. This slide summarizes the adverse event in phase 1 clinical trial for angiosarcoma. High incidence of adverse event is hyperbilisemia, but it was relieved without any treatment. From the previous report about BNCT for head and neck clinical trial, 86% of the patients experienced hyperbilisemia. Additionally, previous report from the conventional radiotherapy showed dose for hyperbilisemia is 0.5 to 1 grade delivered to the cerebral gland. So I think that it may not be specific adverse event for BNCT. So we perform the dose evaluation for typical OAR in case of scalp angiosarcoma. From this table, delivered dose in parotid gland exceeds the threshold dose for hyperbilisemia. Therefore, the hyperbilisemia occurs due to the dose of cerebral gland. Actually, we focus on the brain. From previous report, threshold dose for the brain necrosis is 30 gray equivalent in BNCT and the 20 gray with receiving more than 10 cc in conventional radiotherapy. From this table, delivered dose to brain was within the threshold dose, and the brain necrosis did not occur in BNCT. This is the phase 1 summary for angiosarcoma. In treatment outcome is good response rate and excellent QA. Severe adverse event is asymptomatic hyperbilisemia, but it was resolved without any therapy. And it was comparable to the JSMP study. It was the head and neck BNCT using the new cure provided by the Sumitomo Heavy Industry. Next topic is phase 1 clinical trial for thoracic tumors. BNCT is generally single fraction treatment with one beam direction. Hence, penetration depths of neutrons and therapeutic efficacy are limited. And the thoracic tumors are often deep-seated tumors, especially for esophagus and lung. Furthermore, there are few reports of BNCT for thoracic tumor or irradiation by multiple field. Therefore, to discuss the feasibility of BNCT for thoracic tumors, BNCT treatment planning study for thoracic tumors were conducted. This is the outline of this planning study. First, single fraction treatment planning for all patients were conducted. Table 1 summarizes the treatment planning details. 40 patients were enrolled in this treatment planning study. 6 is the breast, 5 is the lung, and 3 patients with esophagus. So the evaluation was the RB-weighted dose. Right figure shows the scheme of the planning, treatment planning study. And in the second step, to improve the minimum dose to GTB, two-field treatment planning for 6 patients were conducted. Second, in this treatment planning, 6 patients enrolled in this treatment planning study. 1 is the breast, 4 is the lung, and the 1 patient with esophagus cancer. The scheme of the second step is lower figure. There are 2 dose prescription. One of them is the maximum dose of skin is 80 gray equivalent. The other is the mean dose of the liver is 5 gray equivalent. In case of dose constraint of liver was not satisfied when prescription dose 1 was adopted. The prescription dose was changed from 1 to 2. In both 1 field and 2 field cases, above prescription was assigned. Dose of GTV and OAR, such as the liver, heart, and lung, was evaluated. Those calculations were performed assuming a prolonged concentration in blood of 25 ppm. Equivalent dosing to fraction was used to apply the same dose constraint to both 1 field and 2 field cases. Step 3 summarizes the dose calculation factor. CBE for GTV and lung, heart, and liver was assigned separately. Table 4 shows the dose constraint for GTV and liver, heart, and lung. This slide shows the result of dosimetric parameter for thoracic tumors. Table 5, upper table, shows the dosimetric parameter in AQD2 dose in field 1 in 1 field plan. The rate of the satisfying the dose constraint of GTB is only 57.1%. However, using the 2 field, the rate of satisfying the dose constraint of GTB could be improved, and its rate is 85%. This slide shows the example of the dose volume histogram in patient with esophageal cancer. Left side figure shows using a dose volume histogram for using 1 field plan. Right side figure shows the DVH using the 2 field plan. From these figures, using the 2 field plan, conformity was improved. This slide shows the example of tumor dose distribution for a patient with the esophagus tumor. Left side figure shows the 1 field plan. Upper one is the AP beam direction, and the lower one is the PA beam direction. And the right side figure shows the 2 field plan. From this figure, those coverage was improved by using 2 field plan. This is the example of the tumor dose distribution for a patient with a large breast tumor. Left figure shows the 1 field plan, and the right figure is the 2 field plan. From these figures, using 2 field plan, it can be improved the coverage for GTB. and sufficient dose can be delivered to the tumor. From these results, feasibility of BNCT for thoracic tumors was validated. Considering two-field plan for thoracic tumors, it would be possible to treat tumor which is situated deep like esophageal cancer and lung cancer. It would be also useful for large tumor using two-field irradiation. This is a summary in this topic. We finished the phase 1 clinical trial of accelerator-based BNCT for cutaneous melanoma and angiosarcoma. Patient entry was completed for the phase 2 clinical trial of accelerator-based BNCT system for angiosarcoma. And a new phase 1/2 clinical trial for thoracic tumors are now ongoing in our hospital. Next is the implementation accelerator-based BNCT system into hospital. This is a sample schedule of BNCT in our hospital. 2 weeks before the irradiation, we start the treatment planning procedures. We spend about 3 days to determine the treatment planning conditions such as irradiation angle. It calculates some patterns after some patterns. After them, final dose calculation is performed for 4 days to calculate the whole body dose calculation and evaluation. After the final dose calculation, medical doctor and the medical physicist review the dose distribution on a patient, and if it is suitable for a patient, treatment planning is approved. Procedures for quality assurance and control for peripheral device are performed at 1 week before the neutron irradiation, and 1 week after the treatment, the patient discharged. This slide shows the typical treatment procedure for BNCT. We are following the procedures of Kyoto University method of BP administration. 2 hours after administration of bone drug, blood bone concentration measurement, decrease infusion speed of bone drug, and then irradiation as performed. Post-treatment dose evaluation are based on the measured blood bone concentration. This is the sample movie for the treatment today procedure, but there is no audio. Please see this movie. To implement BNCT into hospital, there are some problems. The main two problems are described here. One is the lack of knowledge about BNCT in the medical staff. The other is that there is no standard clinical procedure. To be successful treatment, standard procedure is established and shared among the medical staff. We should discuss how we would like to perform BNCT. For example, when drug is bolus or continuous infusion, the monitor unit of the system is determined by the blood concentration on the treatment day or not. Thus, we have to create the clinical protocol. In our institution, the clinical trial is established based on that in the reactor-based BNCT. To follow the clinical protocol, multiple dry runs were conducted in our institution. Through the dry run, we improve the staff knowledge about BNCT, clarity roles, and the responsibilities in each staff, and create the environment for performing BNCT. It is useful for the conducting runs that process map and workflow are utilized. Based on the process map and workflow, discussion can be performed. And it can be associated with the reduction of human error. Furthermore, it is utilized for the risk analysis in each procedure. This slide shows the process map on the treatment day. First, I performed the daily QA and QC. It was comparable to the conventional radiotherapy. After them, patients arrived in our hospital. After them, we started the drip, the volunteer drug. During the drip volunteer drug, we start the image guidance and the patient transfer patient to the treatment room and determine the monitor unit based on the bone density measurement in blood. After them, we approve the treatment plan, and the approved plan is transferred to the treatment device, and we can perform the BNCT. On treatment day, each occupation is about 4 to 5 hour work. I show you the workflow in our hospital. This workflow is set in each related occupation. The procedure begins 4 hours before the neutron irradiation. The time schedule is structured in each 15 minutes. As mentioned before, there are a lot of work in each occupation. In the draft of the workflow, the time schedule is structured in each 30 minutes. However, it is not sufficient for BNCT. In the latest version of workflow, the time schedule is changed from every 30 minutes to every 15 minutes. Using the process map and workflow, risk analysis is performed based on the task group report 100 in our hospital. To perform risk analysis, brainstorming is performed in related occupations. Method of the risk analysis is failure mode and effect analysis, FMEA. We specify the failure mode, and those are then classified from low to high risk failure mode. Furthermore, countermeasures are taken based on the risk level. The high risk failure mode is assigned based on the scoring. The scoring in each in each failure mode is performed with the 3 components. The total score is calculated by the product of their 3 components. The 3 components are occurrence, severity, and detectability. The total score of product of their component is called as risk priority number. Here I show you the description of occurrence, severity, and detectability values used in TG report. Objective in FMEA is the reduction of RPN value to provide treatment safely and effectively. To reduce the RPN value, activity focuses on the reduction of both occurrence and detectability score, because the severity is uniquely determined and is not improved. This slide shows the result of FMEA on the treatment day procedure in our hospital. It was performed based on the process map. The number of identified failure mode is 16.5. Among them, BNCT specific failure mode reaches 43%. Furthermore, the number of identified high-risk failure mode is 47. Among them, BNCT specific high-risk failure mode reaches 49%. As a result of FMEA, standard procedure is required to perform BNCT safely and effectively. If the detailed data is required, you can find the report from Medical Physics Journal. From FMEA, cause of most failure mode is human error, and it is comparable to that of MRT. It reaches about a half of the total failure mode. Compared BNCT with MRT, failure mode associated with hardware and software error is very high. Here, I show you the countermeasure for identified failure mode. Countermeasures of the strict confirmation and education reaches 48.7%. Among them, failure mode associated with the human error is 84.1%. Furthermore, according to right figure, severity of their failure mode is higher than the others, so impact is so high. Therefore, priority countermeasure is required to improve occurrence and detectability. I show you the countermeasure for those failure modes in our hospital. There are 3 main countermeasures. First is a double check. Second is a periodic review of the process. And the last is the development of the software. On this slide, I show you the staff's capability for BNCT. We surveyed the clinical staff's capability and workloads. The candidates are three institutions in which the clinical BNCT is performed. The survey method is questionnaire. It can reveal the duty work and the required labor. This study was approved by our IRB in our institution. As a result, BNCT requires highly specialized and specific work. Even BNCT staff showed bias in their abilities. Therefore, it reveals that the education system and standardization procedure are needed. This slide shows the result of questionnaire. Blue shows the implementer and teacher. Red shows the implementer, and yellow shows the non-implementer. From these figures, even if the medical staff engaged in the BNCT, not all the work, especially for BNCT specific work, could be done. Furthermore, the medical staff not engaged in BNCT also answered the questionnaire. From these results, they could not perform BNCT work, especially for BNCT specific work. This is the summary. The multiple dry runs and other activities based on the workflow and the process map were conducted to provide BNCT to a patient. Establish a safe and effective environment for BNCT through risk analysis. BNCT requires highly specialized and specific work for medical staff. Thank you for your attention.
Good. Thank you for the detailed explanation of the BNC practice, Dr. Nakamura. So, yes, one question is there. Is it possible any depth cancer treated by BNCT? As we know, the build-up dose is near to surface. This question is BNCT can apply to the depth cancer?
I think only one field it is difficult for BNCT, for deep-seated tumor. But using two fields, we may, I think we can treat them.
Okay, another question is what are the advantage of using a vertical beam compared to the horizontal beam at BNCT?
In my opinion, I think thoracic tumor is very useful, but the brain tumor, I think horizontal beam is suitable.
Okay. And so another question is up to which how depth that we can apply BNCT? I think 5 centimeter or 10 centimeter.
In one field, using one field, I think 6 centimeter, but using the two field, maybe 10 centimeter and so on.
Okay, so from me, I have one question. So usually, how long it takes to deliver the neutron beams? 1 hour?
For angiosarcoma cases, we usually 45 minutes.
45 minutes.
Yeah.
Okay, so how do you control the dose?
Based on the number of neutron and
Number of
the,
neutron.
yes,
Yes.
but the we don't directly measure the neutron, but we measure the proton, but
Current of proton. Yeah.
current of proton.
Okay. And
Through non-clinical trial, the relationship between the neutron and proton was could be investigated. Using the relations, we control the neutron.
Okay. Thank you. And another question from me. So, yes. So, do you use only the BPA?
Yes, I use
You don't use
only
BSH?
I don't use the BSH.
Is there any reason?
I think that the investigational fee for development of drug is very expensive. So we can use only one drug.
Okay. Yeah, some BNCT trial, so they use both BSH and BPA. Yeah, mixed of the BPA and BSH. Yeah, just I heard from another institute. Okay, so if possible, I would like to know about the stability of accelerators. So, did you have any experience of unstable status of accelerator during the irradiation? It is not easy to answer.
During the clinical treatment, we can't experience any problem in accelerator, but the in non-clinical trial, we experience the any trouble in the accelerator.
Okay, so final question is, how often do you replace a lithium target?
After the 50 patient treatment, it may be half of the year.
Half of the year. Okay, thank you very much. Yes, thank you very much. Yes, I'd like to move to the third lecturer. And the third lecturer is Professor KUMADA. He is director of Proton Medical Research Center, Institute of Medicine, University of Tsukuba in Japan. And he is a famous researcher who developed the planning system for BNCT. So, Dr. KUMADA, could you share your presentation?
Thank you for that.
Please start.
Can you see these presentations?
Yes, yes. Okay, please start.
Just a moment. Please wait. Okay, let's start. So thank you for the kind introduction, Sensei, and thank you for giving me this opportunity. Okay, I stopped the video. I concentration my presentation. So I'm Hiroaki KUMADA in Proton Medical Research Center of the University of Tsukuba, Japan.
At present, I'm engaging in the job for the clinical trial of BNCT using our accelerator-based treatment device. In today's lecture, first, Professor Sakurai Sensei introduced the principle of BNCT and clinical trials into BNCT using research reactors. And next, Dr. Nakamura Sensei introduced the equipment at the Cancer Research Center and spoke about actual BNCT treatments and clinical research. So it was very interesting. In my presentation, I will introduce accelerator-based BNCT treatment device, which expected to become more widespread in the future, instead of the research reactors using up to now. First, I will explain how to generate neutrons using an accelerator. Then I will introduce the development status of accelerator-based BNCT treatment devices in the world, including in Japan. Finally, I will give an overview of the treatment device at University of Tsukuba, where I engage. So this slide shows the clinical trials results by using the research reactors. So the left picture shows the malignant brain tumors performed in our University of Tsukuba. And the center of this picture is a very famous picture. So for the first recurrent head and neck cancer patient performed in Kyoto University reactor in 2001. So this is the recurrent case. So this patient already received the conventional surgical operation and X-ray therapy and chemotherapy, but unfortunately this patient recurrent. So the Kyoto University and Osaka University group tried to apply the BNCT. So it's success to treat this patient. So this patient, this result presented in International Congress for BNCT in 2002. After that, the BNCT, the main BNCT is changed to the head and neck cancers. So the right picture shows very impressive pictures for the head and neck cancers. So metastatic malignant melanoma, so the very huge cancers here. So, but this patient irradiated in Kyoto University reactors. So after that, so the almost most tumor disappeared after the irradiation. So very impressive. So, and I showed the map for the reactor-based BNCT facility in the world. So maybe the Professor Sakurai Sensei also already similar map shown. You can see many reactors that have been applied to BNCT research. In Japan, in particular, clinical trial has been conducted using many research reactors here. So, but however, at present, most reactors had been shut down or don't be used to BNCT due to aging and strict the regulations. As far as I know, the only reactor currently conducting BNCT is THOR in Taiwan. I heard that the reactor had planned to register the reactor as a medical device. It's a very challenging and interesting endeavor. So clinical trials of BNCT of about 1,500 cases have been conducted using research reactor in the world. and I believe they have obtained excellent clinical results. Nevertheless, BNCT has not been established and spread worldwide yet. The reason is that treatment required nuclear reactor. Currently, it is not easy to produce and maintain nuclear reactors. And at least in Japan, we cannot get pharmaceutical approval for research reactors. Hence, we can only conduct clinical trials for the treatment. Therefore, BNCT was never established in this situation. To overcome this situation, what method is currently being tried in the world is the method of performing BNCT using an accelerator instead of nuclear reactors. When the development of the accelerator-based BNCT device is succeeded, the patient can receive the treatment in a hospital. Moreover, the device can be applied for pharmaceutical approval. When it realizes, the treatment can upgrade it from the research clinical trials to advanced medical care and insurance medical care. The accelerator-based BNCT is expected to establish and spread worldwide as the type of cancer therapy in the near future. So here a quiz. Neutrons have no electric charge, so they cannot be accelerated in an accelerator, and thus they cannot be given energy. So how do we generate the neutrons needed for treatment in an accelerator? So the answer is that an accelerator is used to first accelerate charged particles such as protons. These accelerated particles are then irradiated onto elements such as beryllium or lithium to generate secondary neutrons. I will introduce the function on each using this animation. So for the accelerator, at present, cyclotron, LINAC, and electrostatic are mainly adapted. For the charged particle, the proton is mainly used. Some groups are also considering using the deuteron. The protons are usually accelerated to 2.5 to 30 MeV. The energy of the proton beam depends on the combining with the target materials. The accelerated protons are irradiated to the target material to generate neutrons. Regarding neutron target material, currently beryllium or lithium are mainly applied to the target material. The target material emits neutrons by the reaction with the accelerated protons. The neutron energy from the target material depends on the material and the proton energy irradiated to the material. However, the neutrons cannot be applied directly to the irradiation for a patient due to high energy, fast neutrons. So hence, the higher energy neutrons released from the target material should be moderated to proper neutron beam applicable to the BNCT treatment by passing through a beam shaping assembly, BSA, consisting of several materials. The neutron beam emitted from beam aperture at the end of the BSA is finally irradiated to the patient. There were major two challenges in developing an accelerator-based neutron generator capable of performing BNCT. The first was the development of an accelerator capable of accelerating high current charged particle. The average current of accelerators for conventional particle therapy is in the picoampere to nanoampere range. On the other hand, accelerators for BNCT need to accelerate charged particle at around 1 to 30 milliamperes. In other words, they had to handle a million times the amount of charged particle. The second challenge was to develop a neutron targeting system capable of irradiating this high current charged particle to generate a huge number of neutrons continuously and stably. When charged particle of the order of milliamperes are irradiated, the target material is received to a heat load of several tens to several hundred kilowatt. Cooling performance is required to withstand this large heat input. Moreover, proton irradiation can be cause a phenomenon known as blistering, in which the material becomes more struggle. Technology is required to deal with this blistering. Furthermore, to apply to treatment, the equipment requires stability, operation, reliability, residual radiation and leakage radiation as low as possible, and accessibility to a patient, easy maintenance, etc. So this slide shows the combination of accelerator and the target material applicable to a BNCT device. So this similar figures already shown by Dr. Nakamura Sensei. So I introduce you again. So first, target material introduced. There are some target materials such as lithium, beryllium, and tantalum, which have the potential for neutron generation by the reaction with charged particle irradiation. In current accelerator-based neutron source for BNCT, lithium and beryllium are usually used. Two figures show the neutron yield for lithium and the beryllium with the proton energy respectively. So regarding lithium, you can see the element has a resonance peak at around 2.5 MeV. Thus, in the case of using lithium, protons are generally accelerated to around 2.5 MeV, and the neutrons are generated by irradiating the protons to lithium. On the other hand, for beryllium, the neutron yield increase in proportion to the energy of proton irradiation, the element here. Even if the average current of the incident protons is the same, the more the proton energy increase, the more the neutron production amount increase. However, the maximum neutron energy also increase. Therefore, in that case, the moderator also becomes to be large to reduce the neutron energy. If you want to suppress the containing contamination of the higher energy neutrons, you should irradiate the lower energy protons to beryllium. In that case, a large amount of protons have to be irradiated to the beryllium due to lower neutron yield. And you should be careful about the higher heat load to the target system. So we have to consider the various trade-offs. For the material point, melting point for both materials, lithium is significantly lower than beryllium. Thus, in the design for the neutron source with lithium using also, you have to consider the heat removable to lithium. And for both materials, the countermeasure for blistering has to be also considered. So this lower table shows the characteristics of several types of proton accelerators that have been applied to BNCT devices so far. Cyclotrons can increase proton energy easily. However, the maximum average current is lower than the other accelerators. LINAC can increase proton energy through the more energy. The larger the size of the accelerator becomes to be large. For the average current of protons also, LINAC can be increased relatively. For the electrostatic accelerator, it can deal with a large current of a few tens of milliamperes. However, in the case of the combination with the large current protons, it is difficult to increase the proton energy. So the electrostatic accelerator has generally adapted the neutron source with the lithium target. This new table shows each characteristics for the combination with each accelerator and both target materials. So when you design an accelerator based on neutron source, you must understand the characteristics of both target materials and each accelerator, respectively, and then select the target material and the accelerator type. So now I would like to introduce the current status of development of accelerator-based BNCT treatment equipment for BNCT. So I'm sorry this slide is so busy. So this table shows the current status of the development of accelerator-based BNCT devices around the world, as far as I know. You can see that more than 20 accelerator BNCT devices are under development and operating worldwide. Recently, there has been particularly high activity in Asia, and including activities that I'm not aware of. There may now be over 30. So you can see from the top this table, many BNCT devices have been developed in Japan. This red, I will provide more details about Japan later. And the middle point, Japan was a world leader in device development with multiple devices already being used for treatment and clinical trials. However, currently, not only in BNCT, but also in other Asian countries such as Korea and China, activities are becoming very popular. In particular, a number of BNCT device developments are underway in China. Detail introduced later. In Europe and the United States also, several devices are being developed, but no clinical trials have been conducted yet. Interestingly, there is no single BNCT facility in the United States. Currently, BNCT research is not being conducted in the USA. However, there are two venture companies that manufacture BNCT treatment devices. And the devices they manufacture are installed in hospitals in other countries. Now let me show you some photos of the actual devices. The picture shows a BNCT device produced by Neutron Therapeutics at the venture company in the USA. The first device of the company has been installed in the hospital of Helsinki University in Finland. You can see that a robotic couch and an in-room CT have been installed in the radiation room. So these advanced technologies adapted in current X-ray therapy combined with their BNCT device. They plan to begin clinical trials of BNCT using this device in the near future. I think this facility will be the first in Europe outside of Asia to conduct accelerator-based BNCT. So the middle picture shows a tandem accelerator-based neutron source installed in Research Institute in Russia. TAE Life Science Corporation, as a venture company at California in USA, has adapted this accelerator and has produced a commercial version of the BNCT device based on the Russian accelerator. And further, the first treatment device of the company has been installed in a hospital in China. So this miracle collaboration between Russia, the USA, and China is probably never going to happen again in modern times, I think. And the second treatment device of TAE Life Science is planned to install in Accelerator Research Institute of Cuneo, Italy. Yeah. So this slide shows 3 projects indicated. So the left top pictures show the tandem accelerator-based neutron source construction in National Atomic Institute in Argentina. And the picture on the upper right from the website of CUNAO, an Italy Radiotherapy Research Institute. As mentioned earlier, this facility will be installed a BNCT device from TAE Life Science. In addition to this, the INFN group is developing a LINAC type device. They plan to install it at CUNAO. And the bottom pictures show a BNCT project in Seoul, Korea. They have also selected the combination of LINAC and beryllium. This combination is similar of our Tsukuba University. They have been conducting clinical trials for recurrent head and neck cancers and recurrent brain tumors using this device since 2022. So this map was shown at the International BNCT Conference held in Poland in June this year by a Chinese researcher. Introduced the BNCT device development project currently underway in China. About 10 projects for the BNCT device development underway. My personal impression is that China is one of the countries with the highest BNCT activity in the world today. So this table was also presented at the international conference and shows detail of the 8 projects. The bottom one, this one, is about device from Sumitomo Heavy Industry in Japan. So detail will be introduced next. This slide shows some representative BNCT project in China that are introduced on the website and elsewhere. So the first left figures show the BNCT facility of Xiamen BNCT Center constructed in Xiamen in South China. So there is near Taiwan. The hospital adapted a treatment device produced by TA Life Science introduced earlier. The schematic image, the facility indicates that there are 2 irradiation rooms. According to the announcement information, several clinical trials at this facility seems to have started in 2022. And this was the first BNCT using an accelerator-based treatment device outside of Japan. The 3 facilities in the middle in China where they are actual developing treatment device for BNCT. It seems that each research institute or university in China is developing not manufacturers but their own devices. In addition, in June 2022 announcement, Sumitomo Heavy Industry made a collaboration with Stella Pharma and a Chinese company to bring their treatment device to a special medical zone on Chinese Hainan Island. This is also worth note. It seems that next year's BNCT International Conference will be held here. So this slide shows the map for the accelerator BNCT facilities in Japan. About 10 devices are installed in some hospitals or universities, and more of the facilities that have completed development are conducting treatment or clinical trials. The 3 facilities in the left, the cyclotron-based device manufactured by Sumitomo Heavy Industry has been installed. These facilities have been conducted several clinical trials. Currently, treatment for malignant recurrent head and neck cancers is being carried out at the 2 hospitals below. This one and this one. And the figure in the top center is the lineup of our Tsukuba group. Detail of the device will be introduced later. And the middle figure shows the dynamitron accelerator for the group of Nagoya University. The device was succeeded to generate enough neutrons. However, it seems that this group will not plan to conduct clinical studies using this device. The bottom center picture shows CACS device installed at the National Cancer Center Hospital in Tokyo. So Dr. Nakamura Sensei introduced at present the group of the hospital is conducting the phase 2 clinical study for angiosarcoma and several cancers using this device. And right top pictures show the BNCT facility at Shonan Kamakura Hospital in Kanagawa Prefecture. This device is the second device of neutron therapeutics. These pictures were taken when I visited the facility last month. Currently, they were making some adjustment to the device. Finally, the photo on bottom right showed the irradiation room of the device installed in Edogawa Hospital in Tokyo. The same CACS device at the National Cancer Center Hospital has been installed. So I'm sorry, this is the Japanese newspaper. However, this hospital had conducted a clinical study on recurrent breast cancer. It's interesting. So currently, various accelerator-based neutron source applicable to BNCT are being developed. At this point, it is unclear which method is optimal. I introduce each method using Japanese devices as example. First, this combination shows a new cure produced by Sumitomo Heavy Industry. Cyclotron has been selected, and the device has adapted beryllium. The proton energy is highest at 30 MeV. Next, this combination shows the CICS device installed in National Cancer Center Hospital. This device has adapted lithium target, and I think the combination and the accelerator selected the LINAC. So I think the combination of these two is a rare case, and the feature on the device is that vertical beam irradiation has been adapted. So as Dr. Nakamura Sensei already introduced, so it's interesting. And next is our case Tsukuba group. Beryllium is used as the target material, and the LINAC is used as the accelerator. The proton energy is 8 MeV, and the average proton current is about 2 milliamperes, both of which are intermediate values. And last one is Shonan Kamakura Hospital. The accelerator used dynamitron, a type of electrostatic accelerator, and lithium is used as the target material. This is a typical combination for a device that used lithium. The left figure shows the neutron spectra of various BNCT devices in Japan. So KUR and JRR4 are reactor-based neutron source. Remains accelerator-based neutron source. The right table shows the characteristics of epithermal neutron beam free in air condition for each BNCT device. Every device has been designed to generate an epithermal neutron beam. As you can see, the spectra for each device are different. The reason is that the proton energy and the target material, as well as the design of the BSA, are different, respectively. And in general, neutron energy and its peak point of the accelerator-based neutron source are tended to be higher than the energy spectra for the reactor-based neutron source. By using both cyclotron-based BNCT devices produced by Sumitomo Heavy Industry and BPA as a boron drug manufactured by Stella Pharma, pharmaceutical clinical trials for recurrent head and neck cancer had been conducted. And based on the results of the study, both the device and the drug have been got licensed for pharmaceutical approval in the spring of 2020. In Japan, at long last, BNCT treatment by combination with the device and the drug for recurrent head and neck cancer began in June 2020 as an insurance medical care. This treatment is being carried out at the two hospitals I introduced earlier. The Kansai BNCT Center in Osaka, which used the device, has reported that they treated 160 patients of the cancer last year. Furthermore, as Dr. Nakamura Sensei also introduced, currently clinical studies on various types of cancers, including malignant meningioma, angiosarcoma, and primary malignant brain tumors, are being conducted at several BNCT facilities. Here, I introduce an activity other than device development. In Japan and elsewhere, BNCT treatment device has been registered as medical equipment under the Pharmaceutical Affairs Law, and commercialization has begun. Based on this, GIEC has begun formulating international standards regarding the safety of BNCT equipment. This standardization work is carried out mainly by Japanese equipment manufacturers. However, some researchers for BNCT, including Dr. Nakamura Sensei and I, are also attending the formulation activity. The first edition of the safety standard is likely to be established as earlier as next year. Furthermore, as the next step, the development of standards for the performance of the equipment has been started in the autumn. Finally, I would like to introduce the accelerator-based BNCT device produced by our Tsukuba group, which I belong to. This is the schematic image of the BNCT device of Tsukuba's iBNCT project. The left top picture shows the building for this facility. Our device has been installed in this building. This facility is not located on University of Tsukuba campus, but a short distance away in Tokai village. The right bottom picture shows the proton linac, and the right top picture is the irradiation room. There is a biological experimental room in the building because we perform various biological radiation experiments for cells and mice. Our project for the treatment device development began in 2011, and we finally achieved the average proton current of 2.1 milliampere in 2019. There are two circular neutron beam ports. And we can select the beam port sites depending on the tumor size. And we also have the extended collimators for irradiation of head and neck cancers. We have confirmed that this device can generate epithermal neutrons of approximately 7 by 10 to the nth under irradiation condition in air. It's enough to apply to the BNCT, I think. So these pictures are of the LINAC accelerator of IBNCT001. Two different types of the LINAC are used to accelerate proton to 8 MeV. The accelerated protons are transported to the beryllium target in front of the irradiation room located on the upper floor. This slide shows the irradiation room and the patient monitoring room. You can see this irradiation room is not as sophisticated as the typical hospital radiotherapy room. The beam port has been set in the center of the shielding wall. And the patient positioning device monitoring cameras have been installed around here. There are many displays, so I'm sorry. The photo on the top left is of the patient monitoring room. There are many displays, so we can see what is happening inside the irradiation room. There is also an irradiation control panel that turns the neutron beam on and off. Medical doctors operate the irradiation and monitor the patient's condition during irradiation. We have developed not only the accelerator for BNCT, but also the peripheral equipment necessary for the treatment. The figures on the left show the screen of the Monte Carlo-based BNCT treatment planning system. Using this system, we can derive the optimal irradiation condition for each patient. The photo on the right shows the patient positioning device installed in the irradiation room. We use a vertical laser light from the ceiling and horizontal laser lights from the both walls to guide accurately and smoothly the patient in the irradiation position determined by the treatment planning system. The photo on the bottom right shows the at the scene of the verification test for positioning using the laser, some laser lights with a head phantom. My specialty is the medical physicist of BNCT, so I was in charge of development these devices. So now please watch this video introduce my business equipment.
Nuclear reactors have been used as a source to generate neutrons. However, as they require complicated maintenance and handling, they're not suitable as medical device and cannot be installed in hospitals. As an alternative to the nuclear reactor, a new approach for practical application of BNCT is a method utilizing an accelerator. Due to the significant advancement of technology in recent years, an amount of neutrons required for BNCT can be generated with a compact accelerator. Based on this technological background, we developed the world's first linear accelerator of about 7-meter length specialized for BNCT with entirely domestic technology. With this linear accelerator, protons are accelerated to about 10% of the speed of light and collide with beryllium to generate neutrons. Neutrons can be generated with the accelerator instead of a nuclear reactor. The accelerator can be installed in hospitals as a medical device, and safe, stable, and simple treatment is possible.
So thank you for seeing the video. So to confirm the performance of the neutron beam of IBNCT-001, we carried out various physics experiments as a part of non-clinical study that required clinical trial. The left pictures show were taken at the scene about the experiment with the water phantom. The water phantom was simulated a human head. In the experiment, we measure the two-dimensional distribution for thermal Newton flux and gamma ray dot rate in the phantom. So the right figure shows the measurement result for thermal Newton flux distribution on the beam axis in the phantom. The maximum neutron flux in the phantom under the conditions of average proton current of 2 milliamperes is approximately 1.4 by 10 to the 9th. So these measurement results proven that our device can generate neutrons with the intensity required for treatment. By using this neutron beam, we can complete an irradiation of a malignant brain tumor is 25 to 40 minutes. As a part of the non-clinical test, we also conducting several tests on the safety of the beam. The photo on the top left shows the measurement of leakage radiation using the whole body phantom. We measured neutrons and gamma rays leaking from the outside of the beam aperture. This experiment confirmed that our device emits little leakage radiation. And the photo on the bottom left shows the measurement of the residual radiation after irradiation. As you know, BNCT used neutrons for irradiation, which caused the device to become radioactive by conducting treatment irradiation. If the radioactivity after irradiation is high, medical staff cannot enter the irradiation room even after irradiation has finished. Based on the measurement, we were able to confirm that the radiation emitted by our device after irradiation is sufficiently low. This means that in the unlikely event of an emergency occurring during irradiation, medical staff can stop the irradiation and immediately approach the patient for treatment. And pictures on the right show the multiple mice being irradiated as a non-clinical study. This experiment demonstrated that our device is biologically safe and can produce a therapeutic effect when combined with a boron drug. So to conduct clinical trials using the device, first we create a protocol in 2021, and we began non-clinical study in 2021 and completed them in the spring of 2023. Based on the results of the non-clinical study, we discussed with the PMDA as a Japanese FDA in 2023. Finally, we have begun a phase 1 clinical trials of this device for the treatment of newly diagnosed malignant brain glioma in January 2024. So the irradiation with the first patient is March of this year. The photo on the left, the dose evaluation screen using the treatment planning system. And the photo in the middle shows the patient being positioned relative to the beam irradiation port. The photo on the right shows the patient monitoring room during irradiation. So the patient's condition is being monitored by medical doctor. Okay, I'm summarize my presentation. So with recent advance in accelerator technology, many accelerator-based BNCT devices are being developed worldwide. The practical application of accelerator-based BNCT devices will enable BNCT to be conducted in hospital, and it is expected that it will be established and spread as an effective cancer treatment method. At present, several clinical trials of BNCT using accelerator-based BNCT devices are being conducted in Japan, China, and Korea. Furthermore, in Japan, BNCT for recurrent head and neck cancer is covered by insurance to medical care and has been treated since 2020. So IBNCT-001, the device of the Tsukuba group, has been completed, and phase 1 clinical study for primary malignant brain glioma is being conducted this spring. Thank you for your kind attention.
Okay. Thank you very much, Professor Kumada. So any question and comment, please pass the chat. So one question from me, and yeah, there are many methods for generating neutron fields. So which method is best, so in terms of the cost for the building facility cost and maintenance cost? Do you think about it?
So maybe it is difficult questions, but I think, in my opinion, maybe the electrostatic accelerator is reasonable than, or Sumitomo Heavy Industry cyclotron is cheaper than the Linux system. Maybe the Sumitomo Heavy Industries cyclotron already produced based on the PET image device, maybe. So they apply to BNCT. So maybe they already commercialized and cost down, maybe success, I think. So, and the electrostatic accelerator, also the peripheral devices smaller than the Linux system, I think.
Okay. So, okay, so I have another question. Yes. And will it become clear? So there are some difference in the neutron energy spectrum by the various method, generated various method. So it can affect the clinical outcomes.
Yes. So the several methodology for generating the neutrons using the several accelerator and materials. Maybe the different is neutron energy. But all device reduce the neutron energy to epithermal neutrons, and the range is 0.5 electron volt to 10 keV. So the almost the same with the neutron energy to apply to the BNCT. So I think the results for effect of the treatment to patient is maybe similar or same with each device, I think.
Okay, thank you. And no question. So, if possible, so I want to get your comment for the development of the drug, including boron. So now is BPA and BSH only the drug. So do you do you have any comment to the development of the drug?
So in my opinion, so the BNCT is a drug cancer treatment. So the neutron is a generate effect of the drug, I think. So that it need to the new drug for boron compound for applicable to the BNCT. So, but unfortunately, now we use only the BPA. So BSH is not. It's difficult to get the pharmaceutical approval. So the BSH cannot apply to the treatment with the accelerator-based BNCT. So we only use the BPA. But in many new, in Japan, as well as in the world, new boron drug are being developed, the several institutes. I hope to success to the development. So the before Nakamura sensei asked the boron several the depth of the treatment depth for BNCT. If we can get the new drug, so the boron concentration is higher than BPA, so the neutron irradiation depth is more deeper. We can apply to the deeper cancer treatment. I think, I hope.
Okay, thank you very much, Professor Kumada, and thank you very much all lecturers. Okay, so I'd like hand back to the Professor Jean. So, do you have any information to the participant, Dr. Jean? No. So please chat. Please see the chat information for you to get the participant certification. So there is a link. Okay. So thank you very much for the every. Oh. Oh, there is one question. So is it possible to apply proton beam and BNCT at a time? Or yeah.
For me. So please again the
Okay, please.
question. So proton beam direct to BNCT, this question.
I think so. I think so.
So the some report published from the proton react with the boron 11. So the react with the dose. So, but I think it is difficult to apply the proton with BNCT. But the proton may generate a small the dose with drug.
To my opinion, so the range of the energy of proton is very different.
Yes.
Yeah, for proton therapy, so usually we use 200 MeV, but BNCT is less than 30 MeV. I think, okay. Thank you very much. Okay, so I'd like to close this AFON school webinar. Thank you very much for every participant. So see you next webinar. Thank you very much. どうも皆さんありがとうございました。
ありがとうございました。
お疲れ様でした。
お疲れ様でした。
あ、ちょっと確認したいんですけど、なんか資料がやっぱり欲しいっていう人がたまにいるんですけど、PDF をもらうことはできますか？もうできなければ別にいいんですけど。
この部ちょっと、整理して、PDF は別に送ってもいいですよ。あんまり
あ、
僕
そうですか。まあもちろん、共有してもいいものだけでいいと思うので、ちょっとじゃあ後でメール送ります。で、まあでも、
私
これまで、そういうの拒否してる人もいるので、
私も公開して渡せるものだけセレクトして後で送りますので。
あ、そうですか。お願いしていいですか。
はい。
すいません。まあ、こちらからも連絡いたします。すいません。今日はどうもありがとうございました。
ありが
お疲れ
とうございます。
様でした。